The year was 1972. Humanity looked up at the stars with a fresh sense of adventure. We had just walked on the moon. Now, our gaze turned outward, beyond our immediate celestial neighborhood. We wanted to explore the gas giants, Jupiter, Saturn, and then venture into the great dark void beyond. So, we built two remarkable emissaries, Pioneer 10, Pioneer 11. These were not just machines, they were extensions of our senses, crafted from metal and wire. They were our scouts, sent on a one-way journey into the unknown, destined to become the first human-made objects to leave our solar system. Attached to the side of each spacecraft was a golden plaque. It was a message, a greeting card to the cosmos. A message in a cosmic bottle, hopeful that another intelligence might find it. The launches were a triumph of engineering and human aspiration. Pioneer 10 lifted off from Cape Canaveral on a pillar of fire. It was on a grand tour of the outer solar system, past the asteroid belt. Pioneer 11 followed a year later on a different trajectory. These small, durable explorers performed flawlessly. They sent back stunning pictures and invaluable data. Years turned into decades. The Pioneer spacecraft sailed on, far beyond Pluto's orbit, into interstellar darkness. Back on Earth, scientists at NASA's Jet Propulsion Laboratory continued to listen. They tracked position and speed with incredible precision, measuring the Doppler shift, tiny frequency changes, calculating velocity down to a few millimeters per second. But a strange pattern began to emerge. Something was wrong. The spacecraft were not where they were supposed to be. Pioneer 10 and 11 were slowing down, a tiny, almost imperceptible deceleration. As if an invisible hand pressed a cosmic brake pedal. The effect was constant and persistent, affecting both spacecraft the same way. This was deeply puzzling. Scientists are by nature skeptics. Their first instinct was not to question the laws of physics, but to question themselves and their tools. Teams of physicists and engineers pored over the code, checking every single calculation. They reanalyzed decades of data. Could it be a problem with the Deep Space Network antennas? They checked the timing systems, the atomic clocks, and the calibration of instruments. Everything seemed to be working perfectly. The next logical step was to look for a problem with the spacecraft themselves. Could they be leaking gas? A tiny, unnoticed leak from a propellant tank or thruster could act like a small rocket, slowing it down. The engineers checked the records. Any gas leaks would have been random and sporadic, not the constant, steady force being observed. Every conventional explanation was systematically ruled out. The force was real. It was not a computational error, a problem with tracking stations, or spacecraft malfunction. It was a genuine physical effect that no one could explain. It was as if a ghost was in the machine, a phantom force acting on our most distant probes. The Pioneer anomaly was no longer just a curiosity. It had become one of the most profound puzzles in modern physics. For the Pioneer anomaly, one of the most persistent ideas had to do with something very mundane: heat. The Pioneer spacecraft were powered by radioisotope thermoelectric generators. These nuclear batteries radiate heat into space. This radiated heat carries momentum. When photons bounce off a surface, they exert a tiny push. If more heat was radiating out the front of the spacecraft, it would create a minuscule braking force. This was known as the thermal recoil force. The inability of simple thermal models to completely explain the anomaly left the door open for revolutionary ideas. What if our understanding of gravity itself was incomplete? One popular idea was modified Newtonian dynamics, MONAD. It suggests gravity behaves differently at very low accelerations, becoming stronger than Newton or Einstein predict. Another possibility? Dark matter. What if a cloud of dark matter sat inside our solar system? Its gravitational drag could slow the Pioneer probes. Even more exotic ideas appeared. Some speculated extra dimensions of space-time. Others wondered if the expansion of the universe itself might influence the spacecraft. Each theory showed human imagination at work. For a time, the Pioneer anomaly was a playground for theorists, hinting at undiscovered laws of nature. Whenever a mystery from space appears, one explanation inevitably captures the public imagination. Aliens. Could some advanced extraterrestrial civilization be responsible? Perhaps our probes had trespassed into a forbidden zone, and an unseen intelligence was gently pushing them back. Or maybe they were being studied by technology beyond our comprehension. This idea was never seriously considered by scientists. Science operates on Occam's razor. The simplest explanation that fits the evidence is usually correct. The idea that gravity itself might be the culprit was a serious contender. If the effect wasn't from the spacecraft, it had to be coming from the space through which it traveled. Scientists took a hard look at Einstein's general relativity. This is our best description of gravity, and it has passed every test with flying colors. The problem with changing gravity is that consequences ripple throughout the cosmos. Any change large enough to affect Pioneer would also affect planetary orbits, which we don't observe. To settle the argument, scientists needed more data. The team at JPL embarked on a massive data recovery effort, hunting down old magnetic tapes from the early Pioneer mission. This was digital archaeology. The old tapes were on obsolete media, and the machines to read them no longer existed. They had to restore a 1970 S-era tape drive. Once decoded, the data contained detailed information about the spacecraft's systems, power levels, temperatures, electrical currents. Exactly what they needed for a precise thermal model. After years of painstaking work, they finally had their answer. The new thermal model was a breakthrough, revealing a crucial asymmetry. Heat from the equipment compartment was radiating off the back of the antenna, which always pointed toward Earth. This created a braking force pushing the spacecraft toward the sun. Once they calculated the thermal recoil force, it was a perfect match. The model predicted deceleration virtually identical to the observed anomaly. The ghost in the machine was not a ghost at all. It was just heat. The smoking gun had been found. And so, the great mystery of the Pioneer anomaly was solved. There was no new physics, no dark matter, no alien tractor beam. The solution was mundane, yet satisfying. It was a triumph of careful, methodical, persistent scientific investigation. The answer was found not in brilliant new theory, but in dusty archives and deep understanding of spacecraft engineering. The Pioneer anomaly serves as a powerful reminder of how science works. A mystery presents itself. We propose ideas, test them against evidence, argue, debate, and dig deeper. The anomaly was not a failure of physics, but a testament to our incredible precision. We are now so good at tracking objects that even gentle push from waste heat becomes detectable. Today, Pioneer 10 and 11 are silent. Their power sources have faded. They are now true ghost ships, drifting eternally through the Milky Way. Moving at 12 kilometers per second, they will take 2 million years to reach the nearest star. They will wander the galaxy for billions of years, long after our sun burns out. They carry their golden plaque, our quiet greeting to the cosmos. The story of the Pioneer anomaly is ultimately a human story, about our ambition to explore and our relentless curiosity. It shows that even in our most advanced endeavors, the simplest things can create profound mysteries. In the quest to understand the universe, every detail matters, and the journey to find the answer is often as important as the answer itself.